So thank you everyone for joining the webinar today. We're super excited to be here talking about simplifying state management and distributed systems. So I'm going to give a few housekeeping items to get us started before we jump into the content for today's webinar. So wherever you are in the world, good afternoon, good morning, good evening. Thanks for being here for this conversation. We expect the session today to go for about 45 minutes, give or take. There will be plenty of time at the end for questions. So please do ask any questions you have in the Q&A panel at the bottom of the screen, and we will get to those questions at the end. We also will have someone joining us today to answer some questions, type answers to some questions as they come up. So this session today will be recorded, and we will be sending everyone who signed up a recording after the event in case you want to take another look at it or in case you want to send it to anyone on your team. So with that, I'm going to go ahead and introduce our wonderful speaker today. I'm your MC. My name is Megan, and I am here joined by Cece. So I'll let Cece say a few words of introduction.
Hi, thanks, Megan. My name is Cece Thompson, and I am a solutions architect here at Temporal. And I'm on the enterprise growth team where my role is to assist customers in designing and implementing solutions using the Temporal platform.
All right, awesome. Yeah, Cece, thank you for the time today. We're excited to hear from you.
No problem.
So actually, before I jump into the content, I wanted to give a quick ad. So in case you haven't heard, we will be having our annual community conference replay in the city of Seattle from September 18th to 20th this September. And I highly recommend that if you're interested in the talk today, you come to the conference. It's going to be an incredible session. We have a lot of amazing speakers lined up from companies like NVIDIA, Salesforce, Cash App, Qualtrics, Netflix, HashiCorp, and that's really just scratching the surface of the awesome speakers we have. Not only that, but you'll have the opportunity to meet and connect with hundreds of other engineers who are interested in using Temporal, are currently using Temporal, and are really just working on some of the, the bleeding edge problems in engineering today. So we are currently doing early bird tickets right now. So if you sign up before July 1st, you'll be able to get a discount. And if you use the promo code webinar20, there is an even further discount that you can get on those tickets. So highly recommend checking that out. You can scan the QR code below or go to replay.temporal.io. All right, so now that I finished that ad, I'm going to pass it off to Cece. I'm going to stop sharing my screen and pass it off to Cece to jump into the content for today.
Awesome. Thanks, Megan. Can you see my screen?
Yep, all good.
Okay, perfect. Awesome. Well, thanks everybody for joining. As Megan said, we're here to talk about simplifying state management in distributed systems. And in order to get started, I want to set the stage and talk about distributed systems and some of those challenges with them. So here we have a pretty simple application that's an order processing system. You can see that in production, it has a bunch of extra pieces to it that are needed to make the system work consistently. And so those are things like message buses, queues, state management, retries, timers. And any of these things can and will fail at any point in time. And developers have to spend their time not only implementing this part of the infrastructure of their system, but then they have to develop for all of the failure conditions that these different components bring into the system, instead of concentrating on the business logic of the system. So how do we solve for these failure conditions without spending hours of development time? So we're going to answer that question along with simplifying state management. So and I want to also set the stage with the application we're going to use for our webinar today. And it's a very simple document processing application. And just a quick note, this application is borrowed from a white paper that one of my colleagues, Mike Nichols, wrote. And there's it's in our resources section of this webinar, and it'll be shared out. That white paper goes into a little more detail of the actual code than we're going to look at today, but we will look at a little bit of code today. So this application is a document processing application. And in this case, what we mean by processing is we're going to both copy edit and graphic edit in parallel. When this document comes back from both of those services, it is then going to move into a published state and then be published. So this is the application that we'll use for all of our examples today. And before we get into the actual application, I wanted to talk about some of the challenges of maintaining state in a distributed system. This is by no means an exhaustive list, but I just wanted to highlight some of the main challenges. So first of all, consistency. Is the state that's being returned older than the state of other nodes in the system? It's very important that every node in the system has to have the same view of the data. And implementing this introduces complexity and possible performance overhead. Fault tolerance. Fault tolerance, distributed systems have to handle partial failures gracefully. Ensuring that transactions can recover from node failures, network partitions, or other issues without losing data or violating consistency is quite complex. Third, we have scalability. Can your system be consistent under increasing loads without performance degradation? And concurrency control. Multiple threads or processes may try to read or write the same data at the same time. And solving for this can be pretty challenging. There are techniques such as distributed locking or timestamp ordering that you can implement, but implementing those in and of themselves is complicated, and they also can lead to bottlenecks and reduce system throughput. And finally, security. Ensuring secure communication and access control across distributed nodes adds an extra layer of complexity. And securing data in transit, ensuring that only authorized nodes can participate in the transactions, is essential for maintaining the integrity of the system. So we've seen some of the challenges. What are some techniques to overcome those challenges? Again, this is not an exhaustive list, just a few I wanted to highlight. So we have local state management, which involves maintaining state within individual components or modules of a system without sharing it with other parts of the application. This is pretty common in front-end development where the UI components can maintain their own state. We also have centralized state management. This is essentially a single source of truth. So there would be a global state store that's shared across multiple components or modules of an application. And this can be common in front-end frameworks where the framework itself is holding the state of the entire, of all the components in the application. And then there's event sourcing and CQRS, which are often seen together. Event sourcing involves capturing and storing changes to application state as a sequence of immutable events. And CQRS separates the responsibility of handling the queries from the commands, so the reads and the writes. And finally, we have state machines, which is what we're going to dig into more in this webinar. So state machines define the behavior of systems based on the current state and the input received. So it's commonly used for business workflows, for instance, a document processing application like we saw in the diagram before, and user interfaces like multi-step forms and even game development, for instance, to keep track of the game state throughout play. So let's look at what a traditional state machine is. So let's start with the definition so we can all be on the same page. So the state of an application can be defined as the current values of the variables at any given point in time of the execution of the application. And a state machine is the programming concept that controls the flow of an application through those various stages and manages how the application responds to input and the transition between those states. So here in our document processing example, we see the different states the document will pass through as far as editable, edit graphic, and then down here we eventually go to a published state. So how would you code this type of state machine? First, we're going to look at a traditional pure Java solution of this state machine. So we start off with a document object, and it's simply a URL to some document and then a unique ID. We also have an enum that holds the different states that this document will pass through as it executes, as the system executes. There is a message queue that holds the transitions between the states of the system. So essentially, when it enters into one state, it is put into the message queue, and then that state is read from the controller, and it knows what to process. So we have our client. This is actually how you start the entire state machine. In this case, we only have a single document. And then it is put on the message queue with this type of event editable. And it's sent onto the message queue. And the controller is pretty much the heart of the entire state machine. So it's responsible for polling the queue to find out what work to do next. So this is a pretty common code construct you see in pure Java state machines. And that's a large case statement that is going through each of the states and then performing some action based on what state it's currently in. The last piece of code we see is what we're calling a state monitor. And this essentially ensures that an event or command is only being executed once. So let's take a look at this. Executing. So you can see the controller is running. It goes into that first event editable. And then you see that it also is entering both the graphic edit and copy edit events at the same time. And then it's waiting to come back from those. Once it comes back, it gets the command publish state, and then the document is published. So that is a pretty simple state machine. And in pure Java, it's kind of a lot of code, right? So a state machine is very complex. It's hard to write and hard to follow the code, which makes testing quite difficult. And modifying it is very challenging. So if we were to add another state, there were lots of pieces of code we had to modify in order to do that. And it also leads to failure-prone code. If it crashes the way that was written, there is nothing saving the state of that system. So all of the state would be lost. In order to save the state of the system, you have to add even more code to make sure that that state is saved off. So how do we fix this problem? So now I'm gonna do a little overview of what temporal is, just to make sure that everybody understands the simple, a high-level overview of temporal. Temporal is a new kind of workflow orchestration tool. So it allows you to code reliable, scalable business transactions without having to worry about queues and events and retries and rollbacks and state. You don't have to think about queuing and eventing and sometimes even databases or state machines. You get all the benefits of an orchestration system without any of the drawbacks. And I'll explain how that works now. So how does temporal work? The first thing you do is you choose one of our SDKs, which are available in Python, Go, .NET, Java, and TypeScript, as well as PHP, not mentioned here. and you write a workflow. And a workflow is the central concept in Temporal, where you define what your end-to-end process is going to look like and what you want to execute. The next thing you do is, also using our SDK, is you write an activity. And an activity is any code that is possibly failure prone. It's the underlying task that you want to perform. So it's essentially something that may talk to a third-party API or connect to a database to get some information about your application, or it integrates with a Kafka topic. And any of these activities with Temporal, we have retry policies. And so if any of those downstream services fail at any time, we can automatically retry them based on the configuration that you put in your system. Once your application is coded, you then deploy it on a Temporal worker. This worker will run your application and captures the state of execution all along the way. Your code is run in your environment and requires no change to how you build and deliver code other than using the Temporal SDK. So you get to keep your same development practices, you keep your same deployment practices, and you keep your same testing practices. The only requirement is that your application is talking to Temporal services over gRPC. So the next step is that workers take direction from the Temporal service for what to do next. The Temporal service captures the state of your application and delivers tasks for your workers to perform. The Temporal service is also where the timers and retries that you set in the configuration get queued. So what happens if your app crashes, or the infrastructure it's running on has issues? In that case, another worker can just pick up the work and resume execution of your workflow by asking Temporal service for the state it was in when that failure happened. So this means that there is no single point of failure in a Temporal application. Both your workers and the Temporal service are designed to be horizontally scalable and fault tolerant. We also have a feature called multi-region namespace, which allows you to define a secondary region for failover purposes. And your workflows are constantly being replicated to that failover. So in case your primary region has an issue and fails, the secondary region will take over immediately and you won't know that anything has happened. So finally, the Temporal's event history enables easy insight and debugging into your application. Every step of your workflow is recorded, and it allows you to trace the entire execution path. We also have a full observability stack on both the SDK side as well as the server side, which allows you to get performance metrics about how your application is performing. So what would a state machine look like on the Temporal side? One second. Of course, I hit the wrong button. Here we go. So in Temporal, we would also start off with the same document object. And then we have an application here that, in this case, we have 3 documents we're sending to it. And we're giving the task queue a name. So in the previous slides, I mentioned that there's a queue on the Temporal service where it tells your worker if there's work to do. So this is the name of the queue we're going to use. This method is essentially setting up your connectivity to Temporal. And this method is what is actually starting the workflows. So it's going through a loop for each of the 3 documents and then creating a workflow and starting that workflow. This method is what is, we said earlier that you basically deploy your code onto a worker. So your worker is what has the context of your code. And this is how you do that. You register both your workflow as well as your activities with that worker. The rest of this code is we have an interface, one for the workflow and one for the activities, and then the implementation. So let's just look at the implementation here. Previously, we said that a workflow executes or has activities in it. So this is where those activities are being configured. And here we're setting the retry option. In this case, we're setting it to just one retry. So if any of the activities we are going to call happen to fail, it will automatically be retried, in this case, one time. And just like the controller was the heart of the system in the pure Java state machine, this is pretty much the heart of the system in the temporal example. So what this is doing is has calls to both the copy edit and graphic edit activities. And this promise is waiting for both of those to return before it continues with the rest of the workflow. So once these both return, it will then publish the document. So you may notice that this code has a lot fewer states than the previous code. And that's because the temporal architecture, we mentioned before that we're abstracting away things like queues. And so those intermediate states no longer need to be explicit. They're implicit in the temporal system by the way it's architected. So let's see this execute. It's here on the right. The logs here are a little bit wordier, but you can see that we're creating, there's pollers that get created for the workflow and the activity. And this is what's actually checking that queue for work on the temporal service. So we're starting the workflow here with this first document and starting the graphic edit, then the copy edit. It comes back from both, and then it starts the publish. And then it repeats for the other two documents. So with temporal, the code was a lot simpler, right? And it says here on the slide, we replace state machines. And in this case, we do. There are some use cases where it does make sense to have a state machine. That's something that you can talk about with any of our solutions architects if your particular use case requires a true state machine. But what we found in many use cases is that temporal really can replace your state machine code. The coding is much easier. There's a lot less of it. That makes testing a lot easier, and it makes modifying and adding different states to your code much, much more simple. Temporal is reliable, and it's since your system is fully orchestrated by temporal, your events and transitions and state management are all taken care of on the temporal side. And it's durable and reliable by default. And so to answer the question about that we asked on one of the first slides about how do we code for all of these failure conditions without spending hours and hours of time, and how do we make distributed transactions more simple to code? The answer is temporal. Thank you for your time. And if you have any questions, we're definitely happy to answer them. And these are the resources I mentioned at the top of the webinar. This is the state machine paper and demo code, as well as a link to sign up for temporal. Megan?
Awesome. We can actually go to questions. We had a few questions come in, Cece, and I think, yeah, if you want to just go back to the question slide, we have one for questions, right? Yeah. Okay, cool. Let's hang on that side. All right, awesome. So we had a few questions come in. The first one actually has two parts, so maybe we should address each part separately.
Okay.
So this person is saying that they understand why someone would consider using temporal if there's a super intricate problem that you're trying to solve. But one of the reasons why engineers like to use distributed systems is because it's scalable, right? So the person's wondering, the first part of their question is temporal distributed and horizontally scalable on its own?
Yes, the temporal service is automatically scalable on its own. So we are hosted on AWS currently. We are going to be expanded to other cloud services. Um, and by default, we are architected to be able to automatically scale and be elastic.
Cool, and horizontally scalable.
Yes, yes, horizontally scalable.
Are there any, do you want to add any more color around the horizontal scalability?
So there's a few different ways. So we can, on your side, you can deploy more workers and we can have more task queues on our side. Um, and all of that is configurable in code. So if you have more workers and more task queues on our side, then you can fan out and have many more processes running at the same time. And we have scaled to uh, our unit of measurement is what's called an action, and an action is basically anything that ends up in a write to the temporal system. So creating a workflow or creating an activity. And we have scaled to, I believe, well over 150,000 actions per second.
Awesome. All right, and the second part of the question is about okay, I think the question went to the answers section. Okay, so Josh actually added some details, some color about the state of the workflows. But yeah, I'll just read it out so we can talk through it a little bit in person. It's easy.
Sure.
So the person's asking, is there a way to tell which data or states belong together and which are fine to end up in different shards? So the person's asking about state management and temporal.
So yeah, so the state of the system, any sharding is handled on the temporal side. So that's not something that is surface to you. You don't have to worry about that because we're keeping track of all of that on the back end. And so all of your state for your particular application will just look like it's all on one shard to you.
Yeah, and the state is kept in workflows, right?
Yes.
Which are organized into namespaces. Um,
Yes, yes. So we have our unit of organization in Temporal is called the namespace. And so while we are a multi-tenant provider, your code is all associated with a single namespace. So that's how we organize and logically separate your code from anybody else's code.
cool, awesome. Okay, we'll move on to the next question. This one's from Joshua. So Joshua was impressed by the temporal code. So he said that it was a little bit automagical to him. So he was wondering if you could walk through in a little bit more detail what the code was doing. So in terms of what was happening with the worker, what does that mean? What does worker even mean? And sort of like maybe just give a little more detail about what happened in that code.
Okay, sure. So you can see the code.
Yep, I can see it.
Okay. So this is the main application. This is just setting up the actual connectivity over gRPC to the temporal service. So you are asking more specifically about the worker. So the worker is what is responsible to communicate with temporal and actually orchestrate when your code is going to execute. So this is what is setting up a worker and giving it a task queue name. And then these couple of lines are giving the implementation of the classes, registering them onto that worker. So it gives the worker context about what code it's going to need to execute. Um, and then this just starts up that worker, the factory. Let me go over here to the workflow implementation. So here is where we're setting up the activity options. This is just a standard. I mean, if you're familiar with Java, this is a standard builder type pattern. So we're setting different options on it. So you can set a timeout. And again, the task queue and activity can have a different task queue name as from a workflow. And then we're setting the retry options. And you can have different retry options for different activities. In this case, we're just using the same retry option for all activities. So on the workflow side, this is executing the copy edit activity in an async manner. And this is doing the same thing. And we're adding it all to an array list, which this is executing. And then this promise is waiting for both of those to return before it continues along in the rest of the workflow. So, and as far as activities, in this particular demo, they're not really doing anything other than writing to the screen, which is what the pure Java was doing as well. But that's why I didn't show it earlier. But it's just writing to the screen. But this is where any actual work, the actual copy edit process would be implemented. Hopefully that answers some of your questions. Feel free to email me if you'd like more details.
Awesome. All right. And we had some follow-up questions about the horizontal scalability. So someone was following up to the conversation we were having earlier, saying that when you say horizontally scale the temporal server, does the temporal server provide inherent clustering mechanisms? Or do we have to rely on a third-party load balancer to scale up temporal?
No, we provide all of that. That being said, depending on the throughput that's expected from your system, we do work with you and make sure that the cell that your particular namespace is installed in is compatible with the requirements that you have. So that's one of the big things that we do with our customers is talk through all of the scaling requirements that they have, but there's nothing specific you need to do necessarily on your side. Again, that does depend on the use case. We do have, for instance, one of our customers is Yum Brands. They all of the mobile orders through Taco Bell go through us. So if you need to scale on the worker side, then that is definitely something you need to take care of on your side as far as scaling. But as scaling on the temporal side is automatic.
Okay, awesome. And yeah, it might also be helpful to distinguish between self-hosting temporal and temporal cloud. So there is a difference there. So if you are self-hosting temporal, you're managing both your workers and your workflow code, and you're also managing the temporal server and responsible for scaling that yourself.
Yeah.
But with temporal cloud, you are still managing your workers and your workflow code yourself in your own environment. But we are fully managing the server for you and dealing with all the scaling aspects to take that off your plate.
Yeah, that's a good call out. I was answering for temporal cloud only. So self-hosted, all of that is is your responsibility.
Yeah. All right. Okay. And we had another follow-up question about the state management. So at state management and sharding. So the person was wondering, they were kind of clarifying from their previous question. They were wondering if there's any way to aid temporal in sharding by telling which data should be sharded together for quick localized access, such as specifying a partition key in Kafka.
Oh, interesting. We don't have anything like that at this point. It's something that we could definitely talk to our product people about. That's an interesting call out.
All right. And we have one more question that we can get to. So this person is wondering, what about a really long workflow that has lots of activities, but small sets of activities could be grouped together by feature and considered as a single smaller workflow. So they're wondering if there's any way to have a workflow that's handling smaller workflows.
Yes, we have several features to do that. So there's something called a child workflow. And as far as a lot of activities, it doesn't matter to temporal. We have workflows that can run for years or run infinitely, even if they sleep for 360 days out of the year. So the scale of that doesn't matter. because we're keeping track of the state. And we wake up your workflow whenever it needs to continue. But as far as having a child workflow, you can have a workflow that calls another workflow. And then that workflow, that's another way that we have for fanning out for larger systems, is that then you can have a child workflow that has its own activities.
Awesome. Thank you. Okay, so looks like we have gotten to the questions that were in the chat. And if you do have any more questions, you can always follow up with us on community Slack. We
I
are
do have
always,
one,
yeah. Oh, go
sorry,
ahead.
Megan, I don't want to interrupt you, but I do have one thing I'd like to add on the sharding question that was asked. Um, so the data that Temporal is keeping for you is more about the state of your application. We're not meant to be the data store of your application. So usually something like making sure your data is put on a specific shard shouldn't matter, because you're only sending us the data that is needed to actually execute that workflow. If you need to store um, data long term and outside of the workflow, that would be something on your side. So yeah, I just wanted to add a little bit of that to make sure it was understood.
Thank you. Yeah, that's a great clarification. All right. Awesome. If you want to go to the next slide. And we already mentioned that, Cece already mentioned this earlier, but a lot of the code that she was showing is linked to from this white paper. So if you're interested, you can see the code in there. And also there's the sign up link for Temporal Cloud if you're interested in that as well. Amazing. And yeah, before we head out, just wanted to give another shout out to Replay. Again, early bird tickets are happening right now. And you can get 20% off with the code webinar20. So thank you, Cece, so much for your time. This was an
All
awesome
right, thank you.
session. Yeah, thank you everyone for attending. And yeah, hope to see you at Replay.